Good morning, everyone. My name is Alon. I work in a company called NoTraffic. I work as an algorithm tech lead. I'm here with Olga. Olga is our simulation engineer. NoTraffic is a technology company that develops a traffic management platform. We are located at singularized intersections. And I'm going to give more detail about the company, but the purpose of this paper and the presentation is to show how we use SUMO in order to solve real-life issues and to support real-world optimization. Let's start with some motivation. So this is an image taken from one of our sensors. What you see here is a bad service of this left turn. This left turn wasn't served well for some time and started to create a spillback. This spillback started to block also the through movement lanes, and in this case, a customer complaint was received, and we had to solve this issue. The important thing here is that once you have a solution, you want to make sure that the solution is valid. You need some kind of a test bed in order to understand that what you're trying to solve will really work in the field. And you don't want just to do like in-field changes to try, for example, to increase the green time for this left turn without being able to assess the effect on other phases or other approaches. So the agenda for the talk will be divided into three parts. First part, terminology. I will show some of the NoTraffic technology and data. We'll talk about ATSPMs. And then the second part will be about how we build simulations in NoTraffic using this data. And we will conclude with a real-world application of SUMO, showing several use cases of how we do it. Okay. This is the layout of our equipment in a signalized intersection. So in every signalized intersection, we install 4 sensor units, 3 standard sensor units, and one of them is a V2X. For anyone who doesn't know V2X is a vehicle to everything, a technology that allows communication between vehicles and the infrastructure, in this case, the traffic light. Also, in every intersection, you have the cabinet. In the cabinet, we install our Nexus unit, which is physically connected to the traffic light controller. This way, we can control the traffic lights. And we also have our cloud-based platform. Every information we detect is being loaded to the cloud, and then data can be shared between intersections. Let's dive in a little bit deeper into what kind of data we have from the sensors. So our sensors are camera and radar. We are doing fusion between the two. We detect vehicles and vulnerable road users like pedestrians and bicycles. The data is being sampled in real time. It's more than 1 FPS. It's 7-8 FPS. We can extract the classification of the road user. For example, is it a car, a bus, a bicycle person, and so on. Some general information about every road user. For example, what is his speed, its lane, distance from stop line. All of this information allows us to build a rich and extensive data set, and this data set is being used also for real-time optimization, for data analytics, and in addition, when we build simulations to create scenarios. We can take this count and create accurate scenarios. Another thing we get from the sensor are the trajectories. So what you can see here in the first image, camera view of just simple approach with 2 inbound lanes. When we do the tracking, we can use clustering in order to cluster all of the trajectories to 3 main clusters, which can be seen here as the turns. So you see 3 clusters, and this cluster is being translated to lanes and connections. So I guess you guys know, from one lane, you can have several connections. For example, if it's a shared movement with right turn and so on. This slide is important because using this data, we can build simulations. So when we have the trajectories, we can build, I will give more details in the next slides, but we can build accurate connections in SUMO. And then we move to SUMO. Let's talk about ATSPM. ATSPM is commonly used measures to assess how well intersections is operating. It stands for Automated Traffic Signal Performance Measures. There is a long list of ATSPMs. We mentioned few more of them in the paper, and we gave a link to the full list. The four we need today for this presentation are traffic counts, how many vehicles crossed. We need the average delay per vehicle. We need the arrival on green. Arrival on green is a measure of progression. So we want to know how many vehicles arrived in the green light, and so they can move on to the next intersection. And split failure. Split failure is a case that a phase is being served, an approach is being served, and then the light turns red while there's still a queue remaining. Okay? So here you can see cars are crossing, but the light turned red, and there are still vehicles waiting. Not so good. Let's move on and talk about how we build simulations using this data I just mentioned. So building realistic micro simulation in SUMO. There are going to be several key steps we talk about. First of all, building the network, the model itself. Then we'll talk about simulation scenario and some challenges there. We'll talk about traffic light controllers and how we simulate them. And we conclude with calibration, how we calibrate our model. This is a satellite image from one of our intersections. This is how it looks like. When we install in a new city, usually it's not just one intersection, it's like thousands of intersections. So we need an automated tool in order to build the simulations. We cannot do it manually. So we tested several tools. One of them is OSM that we talked about here at the conference. In this case, OSM didn't do a good job. You can see one intersection is being split to several. This was what we got from OSM. And what we did, we used the trajectories I showed you earlier in order to try to build the geometry of the intersection. And this is what we got from our data. When you build a network generation, when you build a SUMO network, the sensor gives you several information. For example, the lanes. It gives you the trajectories and the intersection locations. This is translated to SUMO object that you know. It's translated to nodes, which the intersection, edges, and connection. So we use this data in order to build the XMLs for the node, edges, and connections, and we use NetConvert in order to build the SUMO network. And what you can see here from the sensor view is being translated to here. This is already SUMO, and this is the real intersection. Let's talk about scenarios. So we want to build a scenario, like injecting vehicles like to match the real world, but we want the scenario to be we want the count distribution to be as accurate as possible that best fits the field. In particular, what we want to catch, we want to be able to catch arrivals of a group of vehicles called platoons. At the beginning, we took a 1 hour scenario aggregated by a minute, and we took this data, the total count of per minute, and we uniformly distribute along throughout the minute. This yielded the red graph here, which means how many vehicles are in a group. So you saw the biggest group we had is like 10 vehicles, and it didn't match the PM peak or the traffic peak that we measured. So we moved to another method, is to take the counts by 1 FPS. Not aggregating everything, just take the raw data we have from the sensors and building the arrivals accordingly. And in this method, we were really able to catch the big platoons that we wanted to catch. The first method gave us calibration success rate of between 40 to 50%, while the second one gave us between 70 to 80% calibration. It did a great impact. Okay, so we have a model, we have a scenario. Next thing we want to simulate is the traffic control. Here in NoTraffic we have a software. The software, we call it virtual controller, where we can load controller configuration we got from the city. So the process starts, we have a city that wants to buy NoTraffic equipment, and the city gives us the configuration for the controller. Using this virtual controller, we can load the configuration of the controller and be able to replicate exactly how the controller operates in the field and how it responds to every detection and everything. So using the virtual controller, we have the full loop here. So using the scenario, we have road users. Tracy gives us detections. The detections are being transferred to the virtual controllers. The virtual controllers yield traffic signals which have been converted to SUMO links, and then we move to the next. Okay, let's talk about calibration. So when you consider calibration, you need to consider a few things. First of all, what are the metrics that you want to calibrate? Second, what is the car following model that you are going to use? Then some input parameters and the method. So the metrics we chose to use for calibration are the 80 SPMs I presented earlier. The reason for that is that our customer, which are the city, and the experts in the city are the traffic engineers. This is the term they are using. So if you want to speak in the same language as they do, you need to speak in counts, average delay, arrival on green, split failure, and this is the improvement you want to achieve, and this is why you want your simulation to fit best this kind of metrics. Car following model. Olga tested several car following models. The one they chose is Weidemann 99 model. Let's give more details about the input parameters. So here are the input parameters. It's not the full list, but it's a representative list. The standard one are the speed, acceleration, and tau. We found other additional parameters very useful. Maybe you want to try it also in your models. For example, startup delay. Once we tuned it properly, it really improved our simulation. Also the drive after yellow time, because there is a different driver behavior in different cities. Also something to consider. CC2 is the variation of distance I keep from the car in front of me. Okay. The method. Okay, so we have the parameters that we want to tune, the one I just mentioned, and we have the metrics that we want to optimize. So we are using a simple grid search on the input parameters, and for every metric we are giving the error. So the error is measured by, we take, for example, the counts, we measure it in the field, like what is the real number of counts in the city, and we compare it to the number of counts we got from simulations. Also the average delay we do, and the arrival on green we do the same. Since these metrics are not on the same scale, because counts can be like in thousands and the average delay is like thousands of seconds, hopefully less. So first we need to do some data processing, and we need to scale the data, and then we use chi-square in order to assess the error between the field and the simulation, and the error is just simple average on all the metrics we use. So again, we are doing grid search. The set of parameters that yield the best, the minimum error is chosen to be our parameters for calibration. I will show some results of one of our intersections. We'll call it I-57 because it doesn't matter. Here we have the red graph is the simulation, the green graph is the field. Since we want to calibrate, best results are if the bars are exactly the same. Obviously, it's not possible. You cannot completely replicate what's happening in the field. But the results are pretty good. Counts are pretty similar. The arrival on green. There is some differences, but the behavior pretty much is being reproduced. Let's move on to a case study, and this case study will conclude the entire process of how we start from a field issue or from a customer complaint using SUMO, and how we solve it and be able to deploy it in the field. So the steps we use in order to solve a field issue, the first step is reproduce the issue in simulation. Simulation is as good as it reflects real life. It doesn't matter if you got 0 error in the calibration. If you aren't able to reproduce what's happening in the field, I cannot do much with the simulation. So we want to reproduce the issue in simulation. We want to solve the issue in simulation. Now we are in a lab environment. We are in a test bed. We can test several strategies. Nobody gets hurt from it. We are not doing anything in the field until we're sure. Verify the solution is stable and doesn't affect other approaches or other intersections. Deploy in the field with confidence, and monitor in the field to make sure that you really improve in the field. So we are going back to the image I opened with, and this is the split failure or the spillback that we saw in the field. The first thing we want to do is to reproduce the issue. We want to use SUMO in order to get this spillback again in the simulation and to see it. So you can see we got the simulation, we got the spillback. You can also see the 2 vehicles here. These are the 2 vehicles. No, I'm just kidding. It's not that good. This is by chance. But yeah, we were able to replicate the phenomena of the spillback. Okay, so reproduce, check. Next, we want to solve the issue. This goes to our algorithm of how we optimize traffic. We tested several strategies. The one we chose is called Flash Q. In the paper, I give more details. And if you want to know more about how it works, come after the talk and I'll give more details. But you can see the queue that was remaining after the light turned red is not here anymore. Now we want to see that the solution is stable. So we want to make sure that we didn't only solve this one specific case. Here you see a summary throughout the entire scenario, the entire hour. And you see that we're able, also the summary tells us in the macro level, tells us we were able to improve this phase. Another interesting thing to notice is that the other phases haven't been affected that much, which means that in the first place, it wasn't that optimal. We improved all phases. So there was a waste of time, let's call it, or money on the floor, as I like to call it. Here is an improvement of roughly 50%. So now deploy and monitor. This graph are this is not SUMO anymore. It's taken from the field. You see also improvement before we had the solution and after. Here you see an improvement of 43%. So one can argue why in simulation you got 50% and here you got 43%. You're right, it's a good question, but you need to understand the way we were before. Simulation, like 2 years ago when we used it, were completely off, like results completely off from what's happening in the field. And being able to get to these close numbers, 50 and 43%, is amazing. And of course, it means we have more calibration works to do. It's not perfect, but these are good results. Let's conclude. Kiko, quality in, quality out. You have good data, you can build good simulations, and you have good simulations, you can build good optimization or good traffic management. SUMO played a very vital part in our process. Okay, without SUMO, we couldn't test our solution. We couldn't be able we wouldn't be able to know that we are really making a difference, and is integral to our business operations. And I want to show some short video. The video shows 2 other use cases. It's a bit businessy. I'm not trying to sell anything, I promise. But it just shows very nice what we're doing.
like for its residents, autonomously operating the traffic light signal network to maximize efficiency and safety. The results were remarkable, with NoTraffic successfully eliminating a mile-long queue, leading to expansion and the optimization of additional corridors, reducing 75% of average waiting time. Today, NoTraffic optimizes a significant number of intersections